We spent a lot of time talking about double integrals over rectangular regions. So what that meant is we would be given a Cartesian product. So we'd be given R equals A to B for X crossed with the C to D on the Y. So what this gave us is on the coordinate plane, if this is our y-axis and this one is our x-axis, we go from A to B, and here we go from C to D. We're given a rectangle here. We call that rectangle region R. Call that rectangle region R. And then above our region R, we have a function. So there's some height. Which is modeled by f of x, y. So that gives us our height. And then we can find the volume between this rectangular region and our surface that the rectangular region projects onto. But now we're going to think about what happens if I have my xy plane, but instead of a rectangular region, what if I have a general region? So a general region like this domain, D. And this will also project up onto a function by f of xy. And we can find the volume of a really weird looking shape with this domain as its base and then the function as its height. So let's talk about how we're going to do this. We're not going to do any examples today, but we're going to go over some of the theory behind it. So here's our definition. Let's consider a function capital F of x and y, which has is a piecewise function, and it's defined by little f of x, y, if x and y is on the domain D, which is a general region. Otherwise, the function is 0 if x and y are not on the domain D, but are in a rectangular region R. So imagine we have a domain, or a rectangular region R. Here's a rectangular region R. And then inside of that, we have a domain D. There's our domain D, and here's our rectangular region R. So what this says is it says that capital F of x and y is only defined on this domain. On this domain, it's 0. So what it does is it takes a tiny little bit of space so that our function, our surface, is only modeled above the domain D. Otherwise, it's 0. So it models kind of the top of the volume that we're trying to determine. It's just somewhat helpful. So this means that if I take the integral of capital F of x, y over the area, then that's going to be equal to the integral over the domain D of little f of x and y over the area. Because capital F of x and y is equal to 0 over here. So we can make that equivalence. Okay, so now let's cover the types of regions that we can have. Obviously, they're not going to look as crazy as this, but we can model these regions in a special way, especially for while we're starting with rectangular coordinates. So the types of regions that we can have is a type 1 region and a type 2 region. Now let's consider f to be continuous on a type 1 region so that D is modeled by the inequalities such that the ordered pair x and y is such that x is between a and b, and y is in between two functions of x. So y is in between two functions of x. Now how is this going to look? So let's consider that we have this here, we have a here, we have b here, so that's where x's go. And then our y's could be modeled by two different little functions, right? So what we could end up having is something that looks a little bit like this. So it might look, maybe we would have like a function. We would have a function on the bottom, we would have a function on the top. So let me try to draw this out for us. So for a type 1 region, we could have something that looks like this. Have something that looks like that. There's g of x, there's g1 of x, there's g2 of x, and there's a region, but these lines are straight. So this would be one domain. Another option is we could have a domain that looks like this. Could look like that, and they intersect at some point, but the x values are still mediated between a and b. So any integral could be cut out by x values very easily. Now we also have the option where we have so in this case we would take the integral over the domain of f of x and y dA as being the integral between a and b, then the integral between g sub 1 of x and g sub 2 of x of f of x y dy dx. So now consider this iterated integral. We would have y and f of x and y. The first integral would generally be pretty easy, but then when we do the fundamental theorem of calculus, instead of plugging in numerical values, we're plugging in functions. So you'd imagine if these functions are complicated, and the antiderivative of this with respect to y is also complicated, then you get a really complicated integral that you need to do, and then you take it between two numerical values. Now let's consider f being a continuous function on a type 2 region, such that the domain is modeled by ordered pairs x and y, such that h sub 1 of y is less than or equal to x is less than or equal to h sub 2 of y, and c is less than or equal to y is less than or equal to d. Now what's this going to look like? Now in this case, we would have something where we would have d here and c here, and then these would be flat, and then these would be functions of x, or these would be functions of y that model our x bounds. So integrate top to bottom, right? So, and then this would be our domain D. So and then of course we would have the analog. We could have like something that looks like a parabola, and then here would be C or D, and there would be C. It should still make sense. In this case, we want to integrate. Oopsies. In this case, we want to integrate over the domain of D, the function f of x and y dA, integrating between c and d, and then integrating between h sub 1 of y and h sub 2 of y, f of x, y, first with respect to x and then with respect to y. So this is how we do these double integrals. Now, the hard part isn't actually performing this. It's not performing this. The hard part is finding your values, right? Because you're going to need to determine intersection points. You're going to need to determine integration bounds, integration functions. This is where the coordinate geometry really comes into play. So we're going to spend a lot of time talking about these general regions, and then we're going to keep talking about general regions, but we're going to consider different coordinate systems like polar coordinates. Say we had our general region as a circle, then it would be easier to integrate over polar coordinates as opposed to over Cartesian coordinates. But we'll cover that in a later video. So thanks for watching, and we'll see you in the next one.